most of us will know where inflation, but some things is just to remind in order to understand where we're still on the right path. So first of all, the problem to be solved. Well, what was before the Big Bang, we still don't quite know. But the theory of experimentation allows us to look at this problem from a completely different perspective. Why the universe is homogeneous, why the project, why different parts start forming simultaneously, why it is flat, why parallel lines don't intersect, why the universe is so large and heavy, why it has such a large entropy. To many of these simulation of these particular parts, they are almost equivalent to each other, and therefore sometimes it's interesting to keep track of which of these problems must be solved, what inflation which is not, and how to make it solved. So let me make an exercise right now illustrating this last part, the total mass of the universe, just as a reminder. So the total energy radiation in the universe right now is measured. It's approximately, it's larger than 10 to the 53 grams. It's less than total energy of normal matter, much less. But nevertheless, let's look at this part. And let's see how large this energy was back in time when the universe was very young, when it was at the quantum density. At the quantum density, temperature was approximately 32 orders of magnitude bigger than it is right now. Therefore, each photon was 32 orders of magnitude more energetic. And therefore, the total mass of the universe, just the energy and radiation, if not for inflation, would be greater than 10 to the 85 grams. So the energy was extremely large. If at that time, if we have pressed everything to this point, at that time this energy would be sitting in a fraction of the universe of a size smaller than 1 centimeter. So something collect all of these high-tech explosives to a very small region and then ignite it with a accuracy better than 10 to the minus 4. So that is a technological challenge, but also the question where this energy came from, who gave it to us, and what happens in inflationary theory, or at least some versions of inflationary theory, to allow to explain creation of all these substances of the universe, which contains only 1 milligram of matter or even less. This of course sounds very paradoxical, and if we would not really solving equations and checking that we are not violating any fundamental rules like energy conservation, then we will not believe ourselves with these kind of statements. But the thing is that you have energy of matter and energy of gravity, which is negative, and you have instability regime where exponential instability, anything can go wrong, it goes wrong. If you have instability, typically it's exponential, and that's inflation. With exponential instability where zero, or almost zero, whatever, divides into two parts, exponential as positive matter, exponential as negative energy of gravity, and so we deal with matter very carefully. Many models of inflation, all of these started with models which I would say traditional model 79, where she considered quantum corrections to gravity, created a rather complicated but still working model with a different purpose. He did not want to solve this problem. He wanted to solve the singularity problem. Then Chigusa and Kwan studied perturbations of metrics used in this model, which was the first, first prediction which people right now are finding in these perturbations. But then much better motivation was in the paper by Alan Guth, and of course we're waiting that this model doesn't work. And then I came with this new inflation model, and later it was also written also by Stanford and Albert. So this was new inflation, it did not quite work also later learned. And then there was this chaotic inflation model, which is much simpler ideologically. We do not know yet whether it is possible to include it in the string theory. This will be a separate subject, and I'm sure whether or not the college will be talking to the different versions of string theory. I will only briefly mention that in my talk. But just from the point of view of simplicity, you take a potential which is as simple as that, as quadratic potential, and this model has a huge number of different regimes in it. If scale field is small, then it oscillates here. If scale field is a little bit larger, then it moves down very slowly, and the universe at that time inflates. and small perturbations are produced which are responsible for galaxy formation. If the scale field is even larger, but still below this quantum density limit, then you have a kernel inflation, quantum populations easily jump higher and put you into the state with large energy density. The universe there expands exponentially, and so instead of having the universe looking like a sphere, you have a universe which looks like a fractal, which is a big change in psychology, and therefore this model for a long time people were kind of reluctant to accept. Because it, for the beginning, it was not necessary anymore, all of these things. But then gradually, well, this kind of models where initial conditions were not necessarily thermal, gradually became accepted. This is hybrid inflation model, new idea in the sense that we have two different fields. One of them, I mean this height, is responsible for inflation, and another one is responsible for end of inflation. And because you have this distribution of obligations, this model allows to produce perturbation with slightly different spectrum. In some of them you could obtain in blue spectrum. So it was a different interesting class of models. And many models for string inflation are based on structures of this type. So it's just a list. This is a picture, this is a modification of what we had seen before. So these parts are WMAP points. These parts were produced by Akbar experiment. And what we see is that these parts will nicely, these points are lying on the prediction for inflation, except for this part which we already discussed a little bit during the conference, and I will say also a few words about it. And these are very high multiples, and still here you have to the accuracy with which the experiment goes, still quite nicely. I mean, we will watch for one satellite to check whether everything is fine there or not, because accuracy is still not quite sufficient. But nevertheless, it could be completely out of whack. That's what we see right now. Basic predictions of inflation. I'm rushing through it right now because I want to finish the standard part quickly and then go to something more new. So the universe should be homogeneous, isotropic, and flat. And now we should say, well, what about flatness? Somewhere in the year 90-something, 94, 95, 96, people were quite worried because at that time it was said that omega is equal to 0.3, and all of us were trying, well, after the guidance of Neil Durek, trying to construct a model of inflation which would produce you non-flat universe. Somehow managed to do it, and I also tried to do it as well as I could. And what was interesting there, after about 2 years of, well, first we were moderately enthusiastic that it's possible to do it, then we became gradually more pessimistic, and then we understood that none of these models really work. I mean, there is one model out of all of our years of effort works, and this model is extremely ugly. And I can really honestly tell you that this is ugly because I'm a scholar. I know that it's ugly. Well, so after that, we say, okay, well, what can we do? Or maybe we do one. That's what we see right now. It is also isotropic, and it is flat, and the flatness going closer and closer to 1, of course, because of dark energy or whatever works like dark energy. Now, replacement interpretation should be Gaussian, adiabatic with flat spectrum. You can find models where they are non-Gaussian, non-adiabatic, non-flat, it's possible. But generically, in the simplest model, that's what you get. And in the simplest model, that's what you approximately expect in the simplest n² model. And that's what we see right now with this accuracy and experts here in the laboratorium. They, of course, well aware that we should be very careful about really interpreting this 0.02 or 0.015 or whatever is the number. And here also we are going to wait a long time before we really know. But that's nevertheless vicinity of where we are. And then, of course, trying at least to keep ourselves honest, there are some anomalies possibly. For example, at low L, that's what we have seen here. At low L, there is some suppression of signal, And the beginning of this suppression looked catastrophic, then gradually it became okay, well, maybe not such a big deal. Right now we just have a 12 page saying that no, it's not a big deal at all. Whatever it is, I don't know what we have found, because once we have seen an anomaly, we try to find out any kind of resolution, any kind of suppression of law multiples. The only way we have found to have these suppressed multiples and still these other points so nicely aligned on the curve, the only way was multiplying equation with t. We did not find any other way of avoiding equation and still explaining everything. This is maybe more difficult, and also we do not know whether this is real or not. The problem is that it's going to stay with us. The relation of multiples of large L. Maybe we will understand later that this is not serious. Maybe it's just a statistical proof, I don't know. What I know, however, that when we try to explain it somehow, what we want to preserve explanation of all other points here, and then it requires something like inflation. And then we need to add something to the picture which will screw a little bit the part which corresponds to these anomalies. One possibility, for example. It's pathological possibility, but it's possible. Like, for example, if you have discrete symmetry, then you can fall to the right and to the left. Then you have domain walls here. And domain walls are bad if they carry too large amount of energy. But if they are on the MV scale, I don't know any good theory which will produce with this, but well, we will invent it if necessary. So if you have this, then you have domain walls, and typically you have just one or two domain walls per horizon. Because if you have domains, they tend to eat each other, just like with cosmic strings. And then you will have our universe crossed by this domain wall if it is light enough, and that's the condition. Then it will modify a little bit isotope of our universe. Maybe it can produce effects similar to what we are studying right now. Maybe not, I don't know. I don't want to spend too much time thinking about it until it is really getting necessary. But I just wanted to mention that possibilities like that do exist. Now, what about tensor models? Long time ago, I thought that what are our perspectives? Well, if we study a simple model of theoretic inflation n squared by squared, we know the prediction. R, which is the ratio of tensors to scalars, well, R in this model is expected to be of the order of 0.15 or maybe 0.14, depending on how many inflations we are seeing right now in the sky. Is it 60, is it 50? Well, so this corresponds to this point. But then what is interesting is that if you study a model like that, which is just a standard model with spontaneous integration, nothing more. So it's minus n squared by squared here, plus delta phi to the fourth, like Weinberg-Salon model, with, however, sufficiently large amplitude of spontaneous integration. And you consider regime. Here, you can have inflationary regime if this spontaneous integration is bigger than quantum. Or when you are falling from here, you have theoretic inflation as well. And if you point out all the possible values of ratio of R and different values of ns, then what happens is that if in the limit v going to infinity, you will always have this point as in the theorem squared by squared. You will have this value of ns and this value of R. But depending on whether you're falling in this direction or in that direction, if you're in this direction, you for small v, you get the point which corresponds to lambda phi to the fourth theory, because only this part of the effective potential will remain. For large v, it will become as if it were just quadratic, because you will see only this part of the potential. But if you fall from this area, you will have this branch. What I'm trying to say, in the same model, you actually cover all possible values of R from point 3, which is present observational bound, to, well, percent. And this means that even if we not find R in this area, the Planck will fly, and Planck will have approximately, well, this accuracy, and depends on who you are listening. Because some people who do it, they say, we cannot prove that Planck cannot find tensor model. That's a very interesting way of formulating what Planck will discover or not here. But I'm saying that if we will not find R these large field models, you usually have miserably small amplitude of arc, so you're not going to see anything. Okay, so what happens is that in the models of that type, they actually cover the whole range. So it's probably worth spending some money to check what's going on. If you study slightly more complicated models, this is including cubic curve, then actually the corresponding curves, according to these people, cover essentially all allowed area. So you can take any point and you can describe this point by theoretical equation with theory 5 squared, 5 cubed, 5 over 4. Even 2 powers. I don't know where it is root of that, that's the fact. Okay? Now let's talk about alternatives. Yes, because we are also trying to keep ourselves honest with, try to see whether we can do something different. Because why not? I mean, if we learn something smart, and these people are working very hard so that they learn something good. So this is a periodic cycle start with. I call this immortal theory. Immortal theory because it died so many times, it's still with us, so what is one of the problems of this model? One of the problems is singularity problem, because all of these models, most of the alternatives, all of them, they try to, all of these models, they try to avoid singularity. Avoiding singularity is very difficult. I think that singularity problem is a great problem to solve, absolutely independently of any alternative to inflation. If you do it, just fantastic. Okay? Now, on the other hand, what is good about inflation? It solves your problems independently. Whether you're smart enough to solve this singularity problem or not, independently of what is physics near the singularity, or almost independently, depending how long this inflation. And I prefer it to be eternal for them. Now, however, what is the recent incarnation of this? Recent development is called new periodic scenario based on Gauss-Condensate theory, and also there's something, well, with Kurvatons there, because you cannot produce, as we just told the previous speakers, that in this theory, if you do not do anything specific, you get n equals 3, and that's really, really bad. Okay, so what they're adding some extra field there, and this extra field first get isothermal fluctuation sitting on it. Then this isothermal fluctuation are transferred to diabatic fluctuation. It's possible. It's possible, but it's really becoming more and more esoteric and difficult as it was before. Well, I'm not sure. Well, so what is difficult about it? Well, first of all, it's based on the Gauss-Condensate theory. Gauss-Condensate theory was invented by Akani Mohamed and his collaborators several years ago. And if you read recent papers by this group, in particular Akani Mohamed, they themselves say, no, this theory violates null energy condition. This theory cannot be ultraviolet, complete, and absolute theory of what exactly this means. This theory has some problems with black hole thermodynamics, and then people who study black holes say, oh, now I can violate entropy rules. So this is not a nice theory to consider. Well, that's one challenge there. But there are some less esoteric problems with it. If you want to produce density perturbations with class platform, because of this extra field which you add to the theory. Now this extra field, first the universe goes to the singularity, this extra field produces some quantum fluctuations in it. These quantum fluctuations grow, and then you get these perturbations of matrix. Well, the problem is that you must prepare this extra field in such a way that it has no classical perturbation sitting from the very beginning at minus infinity. Why I say no? Because the level of this classical inhomogeneity, if it is above the level of quantum inhomogeneity, then the classical inhomogeneity will grow by the same mechanism which amplifies classical one. So if, amplifies quantum fluctuation. So if you have amplification quantum, if you have classical bigger than quantum, then you are there, you produce completely not class pattern. Therefore, somebody must be assured that when the universe started at minus infinity, this scale field was completely homogeneous. And I do not have any idea how we can do it. Well, I have some ideas. If you take the scenario and do something else to it. Okay, well, so I think that, no. I mean, it's difficult. It is not impossible. It is, you never say some sentences from Churchill, never give up. There's something else which I would show it to you in the sentences from Churchill. Now, there is another thing. The string gas cosmology which Brandenberg has just talked about the previous talk. We spent previous summer together with Mukhanov and Kaufman and Kalkar studying the cycle for papers on the subject. And what we have found after we studied it, and this is our impression, I don't want to go into real probably details, etc. If you want, look what we think about it. What we have found, however, that if you literally take this set of papers, just like a representative of the whole direction, and then you check what is step 1, then you will find that in these papers, instead of ns equal 1, as was applied in this paper, you actually get ns equal 5. Now, maybe it is possible to modify these papers and in order to come to some conclusion. I suggest if you want really to check it, first read it and then read a new set of papers and see yourself whether it's convincing enough. But that's what was kind of the result of very lengthy study of this set of yours. What I should also say that when we try to discuss it with string theory, somehow they are reluctant to look at it because it's not the class of what they are right now studying like string theory, because they do not belong to the class where all moduli are studied like. But that's a separate issue as well. I'm just telling you my impression of what is going on. There are several other suggestions based on mirage cosmology, on quantum cosmology. Well, I got to stop here. I'm just telling that whatever I try to look at, there are some strange things inside the models which require modifications. Now I'm switching towards developing string cosmology. And string cosmology, people were trying to do it for a long time. Now, it was not very easy to do anything good because, well, in the previous version of string cosmology, the volume of compactified space and also the kiloton, they were not stabilized. The kiloton was stabilized by these authors, and volume was stabilized by these authors. And then right now it all goes like one package called usually TTLP scenario, what is also to this figure. And this is some pictures describing what is TTLP scenario. Another talk will tell you much more. What is important is that this is a combination of many different non-perturbative effects all together. First fixing the volume models, then uplifting it here. And what is interesting there, then once we learn how to do it, which was really very difficult. Okay, we thought that maybe people will grab us and find that it's completely inconsistent. At least so far this mechanism, well, nobody told that it is really bad and so people are using it. And if you do it, if you use this mechanism, you start doing cosmology basically, because otherwise it's very hard to make any consistent cosmology since your 6 dimensions, they are not stabilized, so you must explain why you are not in 10-dimensional space. So in this set of models, there are 2 classes of inflationary models. One is modular inflation, where you use only the ingredients which are already sitting in this TTLP constructions, without adding any brains moving in Palladial space. And another is brain inflation, and that is what happens if you have brains and the inflow compute, for example, is associated with the distance between brains. Right now, I'm not going to give any references or detailed discussion of it, since Renato will spend the time in describing it, and to show you a few pictures which are supposed to give some impression of what is going on. This is the first model, which is Patchwork, Kalash, and several other authors here. So that's D3, D7 inflation model. This is the racetrack inflation, which several people who were sitting here in the room participated. And here is DBI inflation. This was proposed by Ivo Silverstein, some very interesting model with non-minimal kinetic terms. One general feature of this model, which however remains not well known until recently, is the following. This basic mechanism of uplifting of PTLT construction was working like that. First, you create this ABS minimum with negative cosmological constant. Then you add to it something, and when you add to it, you produce this minimum, and this is invisibly positive energy, 10 to the minus 120, which is this cosmological constant. Why this? Why all this getting to this 10 to the minus 120? Just wait a little, it will be the one with next transparency. But then, what will happen when you have inflation? You see, what we were adding here to uplift this was kind of cosmological constant, this vacuum energy effectively. But when you try to add vacuum energy, you add this energy depending on what is the volume of compactification. So when you add it, you add a curve, this one, this pinky curve. You add something which is big here and which is a little bit smaller here. So when you add it, you uplift this part by this amount, you uplift this part almost by the same amount, and you almost do not uplift this small part. Okay? So when you add the cosmological constant, which is supposed to bring inflation to you, you are doing something else. You are adding some other field with its own cosmological constant, but when you add the energy, you again add the curve, which on this graph looks like this curve. This is a volume model. This shows you how large is internal space. So as a result, when you add this extra and extra energy, it destabilizes your vacuum which stays here. And the condition for stability, when you work a little bit, the condition for stability is that Hubble constant during inflation must be smaller than the gravitina mass. Now that is very unexpected and very serious in principle. And this is something with formal proof, and I don't think that we want to see it now. But the message is, if gravitina mass is the 1 TeV, which is what many people wanted for many years, then Hubble constant during inflation smaller than 1 TeV, very, very low scale inflation. You will never ever see the gravitational waves from this kind of inflation because the level of R will be 10 to the minus 24. Okay. Nobody even dreamed about measuring this level of gravitational waves. On the other hand, there are some models right now which allow gravitina to be as heavy as 10 to 14 GeV. And then you can possibly go close to the place where you maybe can see gravitational waves. And the scale of inflation will be higher. I'm talking right now, when I'm talking about scale of inflation, I'm talking about the scale of the last stage of inflation, where the gravitina mass was more or less fixed. We're discussing right now with many other people whether it's possible to remove this bound. And in fact, one model where this bound can be removed was suggested by us several years ago. And this model is based on the situation where, without any uplifting, we have a minimum which is here already in Minkowski. And the relation between the gravitina mass and M3 half can be, well, changed very strongly. Still, there is a question whether this model is very fine-tuned or not. So I'm just saying that this is an issue, and this is a very interesting issue. If people will find gravitational waves and we want it to be described by string theory, it will be quite an interesting game, and Renata will tell you much more about that. Now, the new concept which appeared in all these constructions is that when we learn how borrowed a bank from a Spanish person, Shani Thatcher, I asked him, can I borrow your picture? He told me, yes, only if you will let me. So that's what I'm doing here. I've stolen it, but this is the total amount of vacuum which is possible in principle in the string theory because of different types of topologies, because of different types of fluxes. This number of different vacuum. And in some of these vacuum, cosmological constant by chance, maybe just what we see right now. Okay? And if we are in a different minimum, then we are not there because we are there. So that's the main idea, and that fits very nicely in this picture of string theory landscape. To illustrate this, you can think about this like that. you have this kind of degree of 1000 or about vacuum, and we're talking about de Sitter vacuum. If you are an anti-de Sitter, that's the best. But if you're in de Sitter vacuum, which is scenario allows you to be, then you're sitting there, the recording temperature, and it makes you jump, and you can jump to another minimum, then you can return back and jump to another one. Usually these jumps occur well, if it's slow roll, then it is periodic fluctuations. If the walls between minima are quite big, then you jump by producing bubbles, like in all inflation scenario. And then when you are jumping from one minimum to another, you're sitting in the sitter, and the sitter is expanding, and you produce two bubbles, and the bubbles run away from each other because of the exponential expansion of the universe. You still have exponentially large number of space, amount of space, and you jump again, and then in the bubbles where you jump, each of them inside is the sitter, and you jump inside, and inside you produce different bubbles. So then, according to all this, how many it was there? 100 flowers, now become one way or another. You have our universe, which looks approximately like that. In some of the parts, we have floral regime where you have the structure, and we can live there if the technological content there is sufficiently small. In some of them, there is no structure, no life. So that's the structure of the universe. And now, in order to understand where we are and why, we would need to understand how, what is the structure. Because previously an answer was like that. We need to find a theory which explains you the mass of the electron, the mass of the proton, the charge of everything. Right now we have a theory, but we cannot explain much because 10 to the 1000 different minima, each of them has different mass of the electron, different mass of everything. So the goal of science, we have one, this is monotheistic position. We have one God and we must learn how to believe it. Now, here is what we have, this huge amount of different vacuum we must learn in which we live and why. So we have three different possibilities. One, to prove that only one of these minima is actually possible. And this is really challenging, I don't think that it's possible. Another thing, to prove that one of these minima is most probable. Okay? So this is next closest thing to this monotheistic idea. And the third thing is that actually many of them are good and we just happen to live in one. Whether we want it or not, we better try to learn how to count in this. And counting is first to count different vacuums, how many of them, and this number 10 to the whatever years and years. And the second, all of this vacuum is fun. And so you are actually comparing infinities. Infinitely many bubbles of this type, infinitely many bubbles of that type. Maybe this comparison does not make any sense at all, and in this case you just say, okay, we live in our space, that's the end of the story. But maybe, and that's what people are trying to do right now, maybe we can find a way to compare them by studying this process and seeing what is going on when you jump from one minimum to another. One of the problems which appeared recently in the literature, one of these problems is called Boltzmann-Grain problem. Because if we look at the part of the universe right now, then in this part, of the universe where we live right now, we will continue expanding, and then what is going to happen with us? Well, we are going to die because vacuum exponentially expands right now, galaxies run away, energy runs away, but then we'll stay here for infinitely long time, and that just quantum fluctuations may produce peak. So that's called Boltzmann-Grain. If you have no other choice except for what we produce this way, it is still better than nothing else. Okay? But then the question is, so you compare two things. You can jump from the present state. You can jump high enough to start another stage of inflation. And then after this inflation, you produce new regular folks where we're living on the planet and everything. Or you can stay here and jump a little and produce brains from empty state. So you estimate the probability to jump in very, very high, and you find that this probability is smaller than jumping and producing people from empty state. So this is called Boltzmann-Grain problem. you are, well, you don't want to be completely dead, you want to be resurrected. You can't, you're still there. Okay. So now, so this was Boltzmann grains law. And this was announced like Boltzmann grains are coming. Why were not Boltzmann grains? This is a problem we can explain with now what happens is that actually at the same time when we are dying in our empty space and struggling about being resurrected, okay, there are other parts of the universe which are eternally inflating right now as we speak. And these parts are producing normal grains. And because these parts are somewhere here, they're inflating with large speed, then these are beating all of these dead bodies which are rising from the ground. So as a result, good news, if you count correctly, don't worry, well, I mean, we are going to be dead, but next people to come will be normal, real folks, and will be not walking brain. If you count probability, and that is the issue, we must learn how to count probabilities in this eternal universe. And there are some problems with probabilities, and I wanted actually to tell you about some problems about this, and I really do not have any time to do this. Let me just show you the picture, and this picture shows you that if you count something and calculate it correctly, then there is some strange things which appear in your counting, which suggest that your counting is not getting where it's the wrong answer. And then recently, it was possible to suggest some modification of this way of counting and just going quickly to the final result. The final result is that if you were correct for whatever was wrong in our previous thinking about this, you will find some facts which are gauge invariant, which tells you that if inflation is long, then the probability to be there is proportional to the volume of the universe produced by inflation. That's very easy to expect. That's what actually inflation is for. It gives you a lot of space. So if it gives you a lot of space, you reward it. And this means that even if the probability of inflation, to start inflation, is very, very small, then you are rewarded by the exponentially large volume produced by inflation. And well, this is a place where you can stop. This is a place where you can continue. I guess I have 5 minutes now.
No, 5 minutes, yes.
Good. Good. So in these 5 minutes, I will show you how you can apply this idea. Apply quantum cosmology. Okay? Possible application. Let's study theoretical application. Let's study this model, simplest one, and let's add there anything I want to add and see why experimental data pick up this particular model. Do you have any idea, any possible explanation? What, I mean, maybe this is also wrong, because in string theory we still have a hard time getting to anything like that. But if we just think theory trying to analyze it, let's see, well, there are some analysis about all of these numerical quantities. But what is important, I will better skip all these details to go again to the final answer. The final answer for that. If you have theory is square by square, and just measure the total volume of the universe which you can produce by inflation in this theory, then the total volume is proportional to e to the 1 divided by m squared. If you add to this theory lambda part of the force, then you decrease the total amount of inflation unless you choose this lambda to be extremely small. If you add to this theory this term r phi squared, unless this r phi squared multiplied by some coefficient psi, unless this psi is smaller than m squared, and m is 10 to the minus 6 in quantum units. So unless psi is smaller than 10 to the minus 6, you decrease the total amount of inflation. So if you want to have lots of inflation, that's what you want. You want a theory which right now will look like that. Okay? So what does it mean? This means that this model is the best from the point of view of in this class. Okay? From the point of view of producing you what we want to see. And that's exactly this is where it is right now, all depending on to show you the picture maybe slightly in a different format, but still doing relatively well. So this should not be considered as a prediction that that's what we're going to see. Maybe the theory will be ruled out. Ruled out simply because, well, there are different criteria. Simplicity, longevity, amount of inflation, beauty, but then also, well, the hard facts of, well, we want to have it in string theory, it's difficult to have it in string theory. any what you believe. You either have it or not, but this is, this is the best thing we can do at the present moment, trying to learn how to define. Thank you.
Yes, please.
One is to better understand in what sense do you think you have a quantum invariant statement because your normal observers and functional observers?
Okay. I will explain what do I mean by that. Well, complete case invariant. Well, this is a little bit strong statement. What I want to say is that in the previous way of how I myself compare different things, I could cut the universe by the slice of a given time and calculate how many different domains are there in the slice. I could, however, introduce different way of measuring time. Instead of ticking, I could use, for example, distance between galaxies, number of photons. It would produce me different numbers. What we have learned right now, how to avoid this number being so exponentially different. Because previously it was just outrageously bad. Okay? Right now it's moderately different.
Thanks for giving such a lovely talk, and it's always nice listening. I've always been worried with all the problems, all the models which you suggest and which you have suggested since your early days. The problem is very simple. As you know, in inflation, the challenge is not only to get the right density spectrum, but also to produce human beings like us, the standard model parts that are not diagonal. And it's not clear since all your inflation models, including the ones which are given out in split phase ones, motivated ones, are all happening in a hidden sector. So how do you really get that at the end of it?
I'm not sure that I understand the question. In some of the models, inflation happening in the hidden sector. In some of the models, like in this theory amplified to the force, we do not even ask this kind of question. This is a little bit too model specific. Like if you start believing n equal 1 supergravity, then this is a place where you work hidden sector. If you want to produce, if you want
I mean the hidden sector because none of these fields are directly coupled to the standard model, or nor do they carry any standard model charges. How do you really reproduce us?
Okay. So let's divide the different issues into different categories. If you have, say, theory amplified to the force, if you want to couple it to whatever phenomenological field, then it is possible to introduce a field with coupling constant 10 to the minus 6. I know how to calculate, I know how to produce lots of
You do not know the coupling of gravity. You do not know the coupling of gravity.
Sure,
you do it by hand, whatever. So there's a huge uncertainty.
It's a lot of uncertainty everywhere. The question is, does preheating represent a serious challenge to this field? What we have studied, this is a separate issue. What we have studied many models for preheating in this model. We do not see any method of principle challenge of method of principle of you cannot produce field. Sometimes in some string models you actually do have this problem. These problems are separate from the problems how you produce vector overall, and they are solved separately one after the other.
Okay, so my philosophy is not they are not separate. It's just I mean we are keeping them under the carpet and calling them separate.
Okay, great. So if you can produce a model which simultaneously is based on string theory and also we have
I cannot do that for string theory right now, but I can do that for
okay. Good.
Open problems are very important, especially in a deep field, we have not really addressed so far. But there is another question that I have, and it's actually a comment. So I do have to defend the calculation of fluctuations in stringhouse cosmology. If you do the calculations in upon gravity data, then indeed you're likely to get spectrum under time. However, if you do the calculations in data on the components, then you get anything more.
I wonder what is the dimension of this thing about making calculate to spectrum dimension. I wonder why we didn't mention the fact that we're getting n equal 5 under some conditions.
Sorry, I introduced the background in which the whole framework is done. It's done in the framework of the static polygon. I specified that it's
and you postpone it to some